So that's all good. We found out that the exponential function is equal to a power series, just like I was suggesting it is in my previous lecture. And you get a new formula for the number e itself as kind of an added bonus. E is equal to 1 plus 1 on 1 factorial plus 1 on 2 factorial plus 1 on 3 factorial and so on. It's an infinite series equal to the number e. But bear in mind, this is a tool. This is a set of skills. We can now look at a function and figure out whether or not that function could be equal to a power series. And the short of it is we like functions that are equal to a power series. They are very nice to work with. Let's take another example. Here's a function, f of x equals 1 plus x to the power k. And here, k is a real number. So this exponent we're just leaving unspecified for right now. But we already have enough information to start calculating derivatives. That's all we need in order to find Taylor polynomials. And then a Taylor series, all we need is a function whose derivative is something we can compute. And then the derivative of that is something we can compute. And then the derivative of that second derivative is something we can compute, and so on. We need to be able to calculate infinitely many derivatives. And we can for this function. I like to write out the first handful of derivatives just to understand the pattern that's going on. And remember here, k is some arbitrary real number. It may or may not be a whole number. The first derivative of my function is just going to be using the power rule, right? I'll bring down the k as an exponent. I'll have 1 plus x to the power k minus 1. Oh, and I'm supposed to use the chain rule. So I need to multiply by the derivative of the stuff inside, which is just 1. Well, multiplying by 1 never hurt anybody. For the second derivative, I'm going to bring down that old exponent. I'll have k times k minus 1 as my coefficient. I will have 1 plus x to the power k minus 2. And technically, I would have to multiply by the derivative of what's inside. Again, multiplying by 1 never hurt anybody. And so on. So the pattern that I see here is that after taking n of these derivatives, my coefficient is going to be k times k minus 1 times k minus 2 and so on. I will stop when I get to k minus n plus 1, right? I took the first derivative, I stopped at k minus 1 plus 1, which is just k. After taking the second derivative, I stopped at k minus 2 plus 1, which is minus 2. So yes, that is in fact the formula I'm looking at. And then my exponent here will be, I'll have x plus 1 raised to the power k minus n. That's kind of crashing into the formula over on the right side of this slide. So let me isolate that. There's the formula there. Now, I can calculate as many derivatives as I want, as many as I need. I need to evaluate each of those derivatives at x equals 0. I'm looking for a Maclaurin series. That means I'm centering my series at 0. The original function is just equal to 1 when x equals 0. The derivative of that function is equal to k when x equals 0. The second derivative is equal to k times k minus 1 when x equals 0, and so on. Well, I can write that pattern out pretty well. The Maclaurin series is going to look like this. So again, I've got my power series here, x to the power n. times the nth derivative of my original function, evaluated at 0, divided by n factorial. So my summands look like this. Each of my coefficients is a fraction. The numerator looks like k times k minus 1. And I keep putting things in that product until I hit k minus n plus 1, and I stop. The denominator is n factorial. So if I did have a whole number for k, well, eventually, this term right here is going to be 0. Eventually, I'll get to n equals k minus 1, or excuse me, k plus 1. And I will have to stop. That means that my series will just be zeros from then on out, and I actually just have a polynomial. But then for k, which is, if k is not a whole number, then none of those is going to be 0, and we can try the ratio test. So this clip is getting a little bit lengthy. Let's try seeing what that is just next.